All right, so I have to present another one of my students' talks because Jinfeng had some visa issues. So, uh, adaptation of foot placement and center of mass control differs depending on perturbation direction during walking. Very long title. So in my lab, I'm actually interested in trying to understand brain and body adaptations to locomotor perturbations. So I have a recumbent stepper, and we've been using a treadmill, and we are looking at brain dynamics by using electroencephalography or EEG. Now, if you've ever tried to use EEG during walking, it's very challenging because you get a lot of movement artifact. So I've been stuck in this position where I'm constantly trying to improve the EEG technique before I look at my walking data. So I figured maybe I should just look at some walking data without the EEG yet. So we're interested in adaptation, and I use a typical adaptation protocol. So first of all, we have a baseline. So we have these unperturbed steps or strides. And then we have our adaptation period. And here, this is kind of similar to some upper limb reaching sort of adaptation protocols where in every group of 5, one of those is not perturbed. So P is perturbed in green and C is a catch trial. And in the catch trial, it's just we don't apply perturbation. So we do this for about 4 minutes, apparently, and we can look at what happens in the beginning. So when we first introduce the perturbation early, and then what happens at the end to see if they adapt. So that's late. And then after that, we go back where we have no perturbations, and that's unperturbed. And then we can try to look at some after effects. So on the treadmill, in order to do this, we have to use some pretty small perturbations. And so on this treadmill, we're applying the perturbations at the onset is at right leg mid-stance. And in one case, we have what we call a stick perturbation, and that's when we decelerate the belt from 1 to 0.6 meters per second for 200 milliseconds. So it looks like this. Oh, I guess it didn't play. Let's start with this one. Okay, so this is the stick. So in each group of 5, 4 of them are going to decelerate, and 1 of them will not. So hopefully you can see that. And then we also applied a perturbation where we accelerate the belt for 200 milliseconds. And we call that like our slip perturbation. So it looks like that. We wanted these to be pretty short because we wanted the person to be able to return to a normal step before the next foot comes down. So to look at adaptation, we use margin of stability. So for margin of stability, we look at the extrapolated center of mass, which is essentially the center of mass trajectory extrapolated in the direction of its velocity. It's shown in blue. And then we define the base of support. Here we're just using markers on the left foot. So the anterior base of support is defined by the left toe marker, and then the lateral base of support is defined by the left ankle marker, and that's in green. So what are our results? So this is for the anterior-posterior margin of stability, which again, we're taking the difference between the extrapolated center of mass and then the anterior boundary of the base of support. So when we look at the 2 perturbations, we see that when you first introduce the perturbations, that there's a decrease in margin of stability, which is not surprising, what you would expect. And then over time, as they learn to adapt to this, they trend back towards the baseline. And with the margin of stability, we can break that up into the 2 components by looking at the base of support and then the extrapolated center of mass to see if there's any difference in terms of how that margin of stability was changed. So here we don't really see a big difference between those. So from this, we see smaller margin of stability when the perturbations were first introduced, but they adapted towards baseline. We look at the medial lateral margin of stability. So in this case, towards the left side, we see that in the 2 perturbations, we actually get a different behavior. So for the stick perturbation, the margin of stability increased, and for the slip perturbation, it decreased. And then when we look at the left ankle marker and the extrapolated center of mass, we see that they also behave differently. So for the stick perturbation, essentially the foot was placed out a little bit wider, and for the slip, the extrapolated center of mass had a greater component to it, and that's why the margin of stability changed the way that they did it. So take home is anterior-posterior perturbations affected different aspects of the medial lateral control. So the takeaways overall from this project are that there's adaptation of margin of stability to these perturbations. It affected control in the different directions besides the direction of perturbation, because we were doing this in the anterior-posterior direction. And then it seems like it differentially affected the center of mass control and placement. And with that, I'll take any questions and acknowledge my funding from NIH.
Yes. Just have a quick question. On the medial lateral, you showed the margin to the left foot. Which foot? Is that the foot that was being perturbed or the other foot?
Perturbed leg is the right foot. So we only looked at what happened when you placed the left foot.
Sorry, so you're perturbing the right foot, then measuring the margin when you place the left foot.
Yeah. So I get perturbed here, and then we're looking to see what happens where you place your left foot.
Got it. Thank you.
Katie?
When were the perturbations applied during stance?
Roughly mid-stance of the right leg.
Okay. Was it consistently like a certain amount of time after the straight, or just somewhere in mid-stance?
Let's see. He defined a angle, and then once it crossed the threshold, and it was like vertical, then he applied the perturbation.
Is it correct to say that if you had done a stick on the other leg, it would have the same effect as the slip on the left leg? Now, like in these pictures that you're showing on the right?
Yeah, I don't know. I'll have to think about that a little bit more.
I'm curious what your hypothesized results are for the EEG, like once you have that data, and what you're looking for in this study.
Well, we're looking for what brain areas are going to be involved, and since the idea here is to create error and see people learn from the error, then we expect to see the anterior cingulate. And then, depending on the different studies that have been published, there's some thought that maybe the left sensory motor, like the left premotor area, might be a little bit more sensitive to balance demands. So we might expect to see something there. And then in terms of timing, we expect the timing of an increase in, I guess, synchronization in these areas to occur kind of near the onset. And then I sort of hypothesize that with adaptation that would decrease over time.
Since the perturbations are happening almost every step, can you comment as to whether you think it's affecting mostly balance or cost or annoyance, or like, what systems do you think are at play with the adaptation?
Well, the intention was to try to look at balance, because we'll be doing this in older adults as well. So we're trying to increase the balance demands. So whether that really perturbs your balance a whole lot, obviously we don't want to make anybody fall. But I do think it should affect balance in some way. Annoyance, it's actually such a small perturbation, you kind of don't really notice it. You get annoyed by the catch trials. So whenever we take it away suddenly, that's when I felt the greatest, I was most aware that something was going on. In terms of cost, I don't really know. I mean, I'm assuming the cost would go up. And we do have EMG data, we just haven't looked at it yet.
All right, real quick, we do have one spotlight talk after this, so let's not set up, but we can take one or two more questions. Yeah.
Can you tell me what you think your results would be if it had been a more sustained perturbation, such as on a split belt treadmill, where the perturbation lasted the entire stance cycle?
So you mean it's like a continuous perturbation?
Yeah.
So let's see. With respect to what?
schematics of what you're expecting from the EEG.
Oh, what I'm expecting from the EEG. There actually is, there was someone who did EEG during split belt walking. I believe that paper is trying to be published. And I don't know like the final results, but that's when we were having all the challenges of recording EEG. So it's heavily processed. So I don't know. You have to, for a lot of these EEG studies, you have to make your own decision about if you believe it's a true neural response or is it potentially an artifact. So I just think we're not quite there yet with the EEG technology to be comfortable with results in dynamic tasks.
All right, let's thank the speaker.